Hello, welcome back to AE 3530, System Dynamics and Vibrations. In this video, we are going to go over an energy method for deriving equations of motion for single degree of freedom conservative systems. Later, in the following week, we will go over a general technique that uses energy-based methods, or analytical mechanics we call it, to compute equations of motion for both single and multi-degree of freedom systems. However, for SDOF conservative systems, we can derive the equation of motion using the mechanical energy. We're going to consider the following system as an example, consisting of a cart with in this case, a linear spring and a nonlinear spring as well. We're going to we're going to write out what the kinetic and potential energies are, not looking at change in those energies, just what they are in general. So we'll write here T is equal to 1/2 mx dot squared. Here we don't need to deal with the vectors because this is a simple system. For more complicated systems, and when we go through what we call the Lagrange equation, we will look at how you do this in a vector form. And then the potential energy here, V is equal to 1/2 kx squared plus 1/4 alpha x to the 4th. And that's because this nonlinear spring has a force of alpha times x cubed. So the mechanical energy in this case, E, is going to be equal to 1/2 mx dot squared plus 1/2 kx squared plus 1/4 alpha x to the 4th. And this is going to be equal to a constant. We're going to obtain the equation of motion by differentiating the mechanical energy with respect to time. So, again, this is a constant, so we'll do d by dt of E is equal to d over dt of 1/2 mx dot x dot squared plus 1/2 kx squared plus 1/4 alpha x to the 4th. Okay, so we set that E, this is a constant, so this is just going to go to 0. And then we're going to get, by computing the derivative for each term, we'll first have derivative of 1/2 is 0, so we're going to have to do the product rule, mass constant, we have to do it there. So we're going to get m derivative of x dot squared. That's going to be first x dot 2 times x dot, which will cancel the 1/2. We'll get x dot. And then the derivative of what's inside that function using chain rule, which is x double dot. Plus, we'll do the same thing for 1/2 k. We'll get 2x times x dot. So then we'll eliminate the half, and we'll get k times x dot plus, for the nonlinear term, we're going to end up with, taking the derivative, we'll have x cubed times x dot, 4x cubed times x dot, which will eliminate the 1/4. So here we'll get alpha times x cubed times x dot. That's all equal to 0. We can bring out and pull out an x dot. So we'll get x dot times mx double dot plus kx plus alpha x cubed. And that's all equal to 0. Dropping the x dot, we'll find here the equation of motion is mx double dot plus kx plus alpha x cubed equal to 0. And that is the equation of motion for this system. Okay. That is our equation of motion. You can also go the other way to find the total energy. And in fact, you can do, if you have the equation of motion, you can go the other way for both single and multi-degree freedom, and it doesn't have to be conservative either. So let's consider the following system. We're going to go mx double dot plus bx dot plus a times x squared x dot, so that's a nonlinear viscous damping, plus kx plus alpha x cubed is equal to F of t. So we have now some external forcing. We're going to multiply the whole equation by x dot, and then we're going to integrate from 0 to t. So doing so, we'll end up with m x dot x double dot plus b x dot squared plus a x squared x dot squared plus k x x dot plus alpha x cubed x dot is equal to x dot f of t. We're now going to integrate this. We'll write out each term individually. Integrate from 0 to t in this case. 0 to t of mx dot x double dot dt. Or I guess in this case we need a dummy variable, so this will be d tau plus the integral from 0 to t b x dot squared d tau plus the integral from 0 to t a x squared x dot squared d tau plus the integral from 0 to t k times x x dot d tau plus integral from 0 to t alpha x cubed x dot d tau equal to the integral from 0 to t of x dot f of t d tau. And this is actually our equation 32, so I'm going to drag it down here. Okay, so this quantity right here is equivalent to d over dt of 1/2 x dot squared, which is what we saw previously. If we come over to our stiffness term, this quantity here is equivalent to d over dt of 1/2 x squared. And this quantity for the nonlinear spring is equivalent to d over dt of 1/4 x to the 4th. By substituting those in, we will end up with being able to apply the fundamental rule of calculus and eliminate the integrals for the three terms that have green underneath them. And then as a result, we will end up with that we get 1/2 m x dot squared evaluated time at t plus 1/2 k x squared plus 1/4, let me rewrite that, 1/4 alpha x to the 4th plus b times the integral 0 to t x dot squared d tau plus the a times the integral 0 to t of x squared x dot squared d tau. And that's all going to be equal to, or actually, sorry, we now need to have in here minus the initial energy. That's the kinetic and potential energies evaluated at time 0. It's now going to be equal to the integral from 0 to t of x dot f of t d tau. And here we have our kinetic energy. We have the potential energy. We have the dissipated energy, dE. This here is our initial energy. And then the last term is the work done from time 1 to time 2, or from 0 to t we should write actually. In fact, we'll do the same thing for the dissipating energy. This is from 0 to t. This is from 0 to t. So then we can write out that t plus v plus the dissipated energy minus the initial energy is equal to the work done. And I guess we need to add back here these arrows. I missed those. Oops. We need to write from 0 to t minus the initial energy initial mechanical energy is equal to the work done from 0 to time t. And that is known as this whole equation here. This is the conservation of energy. And that concludes this video. Next week we will be looking at Lagrange's equation and going through topics of generalized coordinates, a little bit of principle of virtual work, and then we'll deal with Lagrange's equation, which will provide us another technique for finding equations of motion using energy.